our next speaker, Professor Wiener, will speak about free boundary problems in contact mechanics.
So thank you. And first of all, I want to thank the organizers for giving me the opportunity to come here, the place or the roots of mathematical analysis. What I want to present here is an overview on progress in our ongoing project on problems in contact mechanics. This is work done jointly with my co-worker, Mrs. Nina Ovachova, and also with cooperation with Professor Goodlatte, my colleague and material science at the same university. So this is the outline of my talk. First of all, I want to give you a motivation. I focus here on problems which are characterized by non-monotone stress-strain dependence, so which lead to non-convex variation problems. And the motivation comes from composite structures, from the elimination problems. I will explain to you in a minute. There's a well-known DCB test, double cantilever beam test, and then I'm talking about modeling by sort of variation inequalities, hemi-variation inequalities, where you have analysis on local Lipschitz functionals. And then I want to show you that this modeling can actually lead to a numerical solution. And in the first approach to this, we use the regularization method and for discretization finite element methods. And then I'll show you that this approach works with a very simple numerical example. This is a bilateral contact problem, but with non-monotone friction. And then, if time permits, I want to show you another approach by NDO that stands for non-differential optimization methods. And then I can show you some comparison concerning this DCB test, where I compare both approaches, a regularization approach and the approach coming from non-differential optimization using advanced methods, the advanced method of non-convex bundle method. Okay, here's the motivation. So we have problems very often now in automotive structures and also in aerospace structures, where you have different materials, and these different materials are bounded together, but not bolted, but bolted together by some adhesive. And so as a model problem, you can see it here. Use the pointer here. That is a problem. Here you have two beams here, double cantilever beams. It is fixed here at the end. It is free here, and you pull it out, and between there is this adhesive layer. And so the problem is to study a typical failure model. This is a denomination of these two layers. And from the double cantilever beam test, you get results like that. You get a load displacement curve. So there are three curves here. In the dashed line, this shows you an idealistic situation, namely where you have no contamination. So after an elastic loading up to 150 Newton, let's say, load, you observe an opening of a crack, and the crack steadily grows. But this is not realistic, but you have always some sort of contamination inside. And so what you get, you observe such jumps, such kinks here. What's going on? So you have, after elastic load, here are going up to 150, critical load of 150 Newton. The crack opens, and the structure because of the crack, you observe an increase of the compliance. So the observed load jumps down to approximately 50 newtons, and so the crack stops here. So to speak, it is caught, and then you pull constantly. You pull the specimen, and then with this decreased load, the crack propagates again until this critical load of, let's say, 90 Newton. Again, the crack stops here, and the critical load, the observed load, jumps down to this level of 50 Newton, and so the story goes on. This jumps until you observe a total failure of the structure. You find another curve here. This is a punctated curve. This shows you a specimen with much more contamination. It is not a continuous curve, but it shows macro cracks which are not visible at this chosen scale. So this comes from experiments from our colleagues in material science, and the goal is, well, you want to get more knowledge about the stress field and the complete displacement field. So typically, what you get from experiments you have this force or where you pull. You have here the data, the opening of the specimen, and you observe here a crack length. And you measure here the displacement here at the open, at the free end, but you do not know what's going on here inside the specimen. You do not know the stress field. So this is a time where modeling comes in, and we are modeling this problem by continuum mechanics within the range of linear elasticity. So it's a geometric linearization. You have the displacement field depending on the strain field depending on the displacement field. You have the stress field. You have this gives you the energy form here. You have by loading, you have this out of work here, and of course you have boundary conditions by this fixing here. You have this zero boundary conditions here, but now you have unilateral conditions here in vertical direction, in two-rig direction, so greater or equal 0, and all the behavior of the adhesive layer here will be captured by a non-monotone multivalued adhesive law. That means a typical example is given by that. So we mimic this behavior with the jump. So we describe this in the form of generalized derivative with respect to some non-convex function J, which will turn out to be locally Lipschitz. And of course, such a law between normal stress and displacement, vertical direction too, has to be validated by such testing methods. So the mathematical model is then in Welschel forms is a hemi-Welschel inequality, which goes back to the in this formulation to the work of Panagopoulos in the 80s. So we are doing work in this framework here. You see again this bilinear form coming from linear elasticity, but we have now additional term here, this coming from this non-monotone stress displacement behavior. And we have this inequality constraint, which is captured in this set K subset in the appropriate function space, H1 functions, which are 0 on this boundary part gamma u. And now in more mathematical terms, this J naught is a generalized directional derivative of a Lipschitz minimum type function J. We see in a minute, we see some examples of that. So we can also write this in the form of potential energy. You have this standard linear energy from linear bilinear form from linear elasticity, and you add some function J, which in this framework is called a superpotential, just by integrating up this small j here, and then you can write it down as a problem, situational problems, a non-convex situational problems, as minimizing this function pi, subject to this constraint, which is captured in this set k. And of course, you can write down also optimality condition here with a generalized derivative here, and here with a normal cone to this convex set k. But it turns out for the numerical approach, it is more suitable to use the rational formulation, and so let's describe a more general setting here for the semi-rational inequalities. Again, we have here standard subrotate space. We are describing linear elasticity, so we can go out from a linear continuous operator, which is cursive, by zero boundary condition. You have discursivity, and moreover, to describe this non-monotonicity, you have this non-smooth function. You have, of course, when you use some mathematical assumptions, some measurability assumption, and as told you before, said to you before, we assume this is a locally Lipschitz function, and moreover, you have to use to assume some growth condition, and so you end up with this problem of HVI, hemi-rational inequal problems, and here to write in more precise term, you put in here, because you were working on the bounded part gamma here, you put in here the trace map gamma here, and now the first thing what mathematicians are doing, of course, if this mathematical problem makes sense, so you want to prove some existence result, and this could be done in the framework of pseudo-monotone rational inequalities. What are pseudo-monotone rational inequalities? You have here a function of phi which lives on the product of a convex closed set K, where the phi in the second argument is convex, and the phi in the first argument is upper semi-continuous. You can relax it that this is upper semi-continuous only on fine dimensional parts of K, and the pseudo-monotonicity is written here in this formula. If you consider a sequence un, which is weakly convergent to some u, and if you have this inequality here tested with this limit element u, then you have here this conclusion. Well, this looks a little bit technical, but it mimics the pseudo-monotone operators which were introduced by Précy in the 80s. But you should, we will see here already that it is important here that our function is here only convex in the second argument, because this derivative here, the generalized derivative, is only it's not linear affine but sublinear, so it is convex. And so under this condition you can prove that the original pseudo-monotone rational inequality has a solution, and now because of this implies to our hemi-rational inequalities. And moreover, of course, you want to get under some reasonable assumption some uniqueness, but here you have to use some additional assumptions to cope with non-monotonicity. And monotonicity would say that you have this sum here would less or equal 0, and so you admit here some perturbation, but you measure this perturbation with respect to the norm in V, and then you can catch this perturbation by the norm of the embedding of the trace map, and so you can prove that under such a condition there exists a unique solution. And to give some such examples of such non-convex functions, let's here look at this graph. It is just here you have a maximum here of quadratic functions, which of convex concave functions, and you observe here these are locally Lipschitz functions, and which are regular in this sense. So you can apply the theory just before, and you find that now you find this constant alpha in this way here. And now the problem is, of course, it's a nice model. You can prove existence and under some conditions at least some uniqueness result, but the question is this approach worthwhile to do and interesting enough to do numerical work here to come up with some results. And of course the first problem is here, how to treat such a non-smooth term, and the answer is of course regularize. We are mathematicians and we all like the small epsilon, so you introduce a small epsilon here, and for the first look here, what you can do with such a king, let's think of the modulus function. You can approximate this by a Argus-Tangis function with a right scaling, but let's do it in a more systematic way. You can introduce a smoothing approximation via convolution here, and this term here, with some function zeta, which with some kernel rho here, and kernel function rho here, and so you get a whole bunch of smoothing functions. And the trick is here, you want to regularize such functions, or you want to regularize such functions which are the maximum of two or several functions, and you will not write different formulas for all these. But the trick is here, you use a recursive representation, going back to Berzeker 75, that you can write down such a maximum function only by using the plus function. So what you have to do only is to regularize the plus function. And so this can be done in this way by this convolution here, with some kernel function rho, and so doing this you get a regularized problem. So instead of the j of u, get a j epsilon, and then you can differentiate, and then of course of the new derivative constraint here, which is still there, you get a variation inequality, but it is now a convex problem. And moreover, now in addition to regularization, you have to introduce discretization here. This is done by, let's say, most straightforward way in a finite element approximation based on a Galerkin approximation. And because of these terms here, integral term, you have to use an appropriate quadrature rule. If you use the most simple approximation, piecewise linear approximation, then the suitable quadrature rule will be the Kepler rule here, trapezoidal, and so you end up with a discrete problem, which is with respect to the parameters epsilon and h the mesh length of the finite element discretization, and again you have because of the unique constraint here, you have here then a finely measured variation inequality. So to get here numerical results, you need more steps. You rewrite this as a Kuhn-Tucker system, and you introduce a merit function, but then at the end you can use classic optimization methods to arrive in, for instance, gradient method, or yes, and then you are here to give a basis for this results. You have proven a convergence result here with independence with epsilon h going to 0, and to show you that this approach works, I want to discuss a very simple numerical example. It's a bilateral contact with non-monotone friction here, and so this is only one kink here, and the jump here, only one jump downwards here. So it is simplified compared to the original DCB problem. And then write down the inversion inequality here. And now you see how regularizing works here. You have here, here it is the minimum of two smooth functions, the minimum of this quadratic here, and this linear function, and this gives you this non-smooth, non-convex function, and by one regularization you get this approximation here, and this is now the regularized problem, and again you end up with the discrete problems, and now show you some numerical results with non-monotone friction, depending on the different h here, 2 to the power of minus n, and so for final results you start with here with a rather rough approximation. So we get visibly also some convergence here for the tangential displacement, and also here a picture for the result potential stresses in along this contact boundary. Well, I think I have some minutes time. Some minutes, okay. So there is another approach to numerical solution of these problems. So instead of regulation, try to discretize the problem directly by finite element. Of course, then you end up with non-convex, non-smooth optimization problems, and then, well, then this you cannot lose standard optimization techniques, but you have to use advanced methods of non-divergent optimization. And for instance, well, this is going back to Zove and the French school, Le Marchal, about for convex problems is the bundle methods, but most recently there's work done by Dominique Knoll in the University Paul Sabatier, Toulouse, and we are working together with him to extend such non-convex bundle methods for such problems here. And so these are results like that here. Now we have also now two methods at our hand. We can compare bundle versus regularization, and here you see that it's depending also here on the traction force. Here there's practically there's only linear elasticity behavior. There are no jumps here, but the jumps occur with a higher traction force here, and we have practically coincidence of these two methods, and you see also in the figures the same figures, and this is where I want to stop here. Thank you very much for your attention.
Comments? Okay, so we thank you again.